Welcome to this explainer. Okay, I want you to just take a second and look around you. Literally everything you can see, touch, or breathe right now is chemistry in action. But because the universe of chemistry is so incredibly vast, scientists have had to break it down into specialized branches. It's the only way we can really begin to understand the materials, the living organisms, and the environments that make up our physical world.
So that begs a pretty massive question, right? How do we study absolutely everything around us? Well, we have to divide and conquer. Each scientific branch is dedicated to studying a specific type of substance or chemical process. It gives us a highly structured, manageable way to decode the mysteries of our universe.
To make sense of it all, we're going to break things down from the micro to the macro. We'll start with number 1, inorganic chemistry, looking beyond just carbon. Then, number 2, organic chemistry, which is the chemistry of life. Next is number 3, environmental chemistry, focusing on protecting our planet. And finally, number 4, analytical chemistry, which is all about measuring the truth.
All right, let's jump right into our first foundational block. Number 1, inorganic chemistry. So what exactly is inorganic chemistry? Basically, it's the study of the synthesis, composition, properties, and structure of elements and compounds that contain little or no carbon. In other words, scientists in this field are looking at a material and asking 4 simple questions. How do we make this? What's actually inside it? How does it behave? And exactly how are its atoms arranged?
The crucial point here is that we're talking about the raw, foundational building blocks of the physical world. Things like metals, nonmetals, mixtures of the two, salts, acids, and bases. They're kind of the unsung heroes of matter.
And why should you care? Well, because inorganic chemistry is literally holding your physical world together. We're talking about the heavy iron used in the structural framework of the buildings you live and work in. We're talking about the calcium compounds that make up the thick cement in your sidewalks. It's even the table salt you sprinkle on your dinner. The real-world applications are absolutely staggering. We use these inorganic compounds to formulate life-saving medicines and to create the fertilizers that grow the massive crops that feed the world. We use them as catalysts to speed up complex industrial reactions. They're even the vibrant pigments in the paint on your walls and the protective coatings that stop your metals from rusting.
Okay, so inorganic chemistry focuses on substances with little to no carbon. But what happens when we flip that and shift our focus almost entirely to carbon? Well, that takes us directly across the border, from the inorganic realm into the organic one. And it's a dramatic shift. We are moving from cold, hard metals and salts right into the breathtaking building blocks of life itself.
Which brings us perfectly to part 2, organic chemistry.
By definition, organic chemistry is the branch that studies carbon compounds, specifically focusing on hydrocarbons, which are made of carbon and hydrogen, and their derivatives. Carbon is the absolute superstar of the periodic table here, simply because it can miraculously form millions of different, highly complex compounds. Actually, quick side note, there are a few really simple carbon salts, like carbonates, that act as rebels and get left out of this organic category, but generally carbon is the main event.
So why is carbon such a big deal? Because organic compounds are the sheer essence of life. You'll find them in absolutely every living organism on this planet. They're in plants, animals, and humans. You simply cannot have life as we know it without these carbon compounds. We are literally built out of them.
Just look at how much of your daily experience is ruled by organic chemistry. It's the sugar in your morning coffee and the cotton in your favorite t-shirt. It's the cooking oil in your frying pan, the paper you write on, it's even the petrol in your car and the plastic in your smartphone. It is absolutely everywhere.
All right, now let's zoom out to the macro level for part 3, environmental chemistry.
This branch treats the Earth like one giant interconnected laboratory. Environmental chemistry is the scientific study of the complex chemical and biochemical processes that flow constantly through our air, our water, and our soil. Scientists in this field basically act like environmental detectives tracking chemicals. They follow a very clear process. First, what is the source of the chemical? A factory smokestack, a car exhaust? Second, what chemical reactions is it undergoing once it's out in nature? Third, what effects is it having on the environment? And fourth, what is the final fate of that chemical? Where does it ultimately settle? By tracking these pathways, environmental chemistry becomes incredibly solution-oriented. It's all about deeply understanding both the causes and the effects of pollution, so we can figure out real, actionable ways to reduce it. That is how we protect human health save animal ecosystems, and preserve our vital clean air and water. Let's shift gears to our fourth and final specific branch, analytical chemistry. Now, if environmental chemistry is about the big picture, analytical chemistry is all about zooming way in to find the absolute truth. This branch studies the analysis of different substances to answer two highly specific questions. What exact substances are hiding inside this material, and precisely how much of each substance is in there? So, what does this actually look like in a modern lab? It's a strict, highly accurate three-step procedure. Step 1, the separation of the substances from one another. Step 2, the identification of those specific microscopic substances using advanced instruments. And step 3, the determination of their exact concentration. They map out every single component.
And this perfectly highlights why analytical chemistry is so vital to our everyday survival. When a hospital tests your blood to figure out what's making you sick, that's analytical chemistry. When cities urgently need to know if drinking water is safe, or when facilities verify the purity of our daily medicines or test the quality of our food, they rely entirely on this modern analysis. It is essentially the invisible shield keeping us safe. All right, that brings us to our summary, the chemistry of everything. Let's pull all these ideas together.
Let's do a quick recap to cement this. Inorganic chemistry builds our physical world with elements. Think iron. Organic chemistry fuels life with carbon compounds. Think sugar. Environmental chemistry focuses on the earth to protect us from things like pollution. And analytical chemistry uses perfect precision measurement to do things like test our blood and keep us healthy. The big takeaway here is that chemistry makes everyday life and all modern scientific research possible. These four branches aren't just isolated silos. They work together in a massive, beautiful symphony. They are the hidden engine driving our modern world. We interact with the jaw-dropping results of all four of these branches every single day. So, as you go about your routine today, think about the food you eat, the buildings you walk into, the water you drink. Which branch of chemistry do you think you rely on the most without even realizing it?